So over the past few years, I've been working on a new auxiliary field quantum Monte Carlo technique based upon quantum field theory techniques for the study of ultra-cold Bose-Fermi mixtures and optical lattices. And I bet not any one of you, where's Norman around here now, understood what I just said. And seeing that my advisor over the past 3 years, who likes to pose in front of equations, didn't understand what I just said over the past 3 years, I'm not going to expect you to understand what my day job entails over the next 15 minutes. Instead, I'll talk about a topic that's much, much closer to home and work that I've actually done in DOE labs over the past few months at Livermore, trying to develop a new quantum Monte Carlo technique for high-pressure hydrogen. So I know that all of you are extremely familiar with hydrogen, as it was hydrogen that probably woke you up this morning and probably aggravated you a great deal. However, hydrogen is not just in the sun. It is the most abundant element in the universe, constituting 90% of all of the atoms out there. In fact, the total mass of hydrogen in Jupiter, and I should say the hydrogen in Jupiter's high pressure at that, totals 40 times the mass of the Earth, and perhaps even more. And as I'm sure absolutely every single one of you knows, hydrogen is the lightest and first element on the periodic table. Putting all of these facts together, you think that hydrogen is extremely simple. But hydrogen is actually hardly simple, and many things still remain unknown about hydrogen. This is because of the fact that being so light, hydrogen is the most quantum element on the periodic table. Among its other quantum attributes, hydrogen has a very large de Broglie wavelength, lambda here. The de Broglie wavelength is basically the wavelength of the matter waves that hydrogen produces. And this wavelength, in many, particularly high pressure liquids and solids, is larger than the distance between hydrogen molecules in those materials. Also, for the purpose of this talk, hydrogen has a very large zero-point energy, which means that its atoms vibrate and therefore are extremely hard to pinpoint, even at the lowest of temperatures. These quantum attributes make hydrogen's behavior extremely difficult to predict, but at the same time make hydrogen a prime candidate for a number of fascinating phenomena. In fact, the reason why many people still study hydrogen is because of two predictions that were made over 60 years ago. The first prediction was made by Eugene Wigner in 1935, and he suggested that at very high pressures, hydrogen would in fact become a metal. Later on, Neil Ashcroft went one step further and suggested that hydrogen might also be a high-temperature superconductor under various extreme conditions. These predictions beg the question, what does the hydrogen phase diagram look like? Today's hydrogen phase diagram, the most current version is given here, was produced by a blend of theory and computation. However, I wouldn't take any of the points on this phase diagram seriously because many of these points are still in dispute. What is known is that metallic hydrogen has not yet been found yet, but is expected to be found at low temperatures and high pressures somewhere around here. But as you might notice if you're a keen observer, there are very, very few data points around here. So at low temperatures and high pressures, not much is known. With this in mind, the motivating question behind our work was, can we create a computational technique that is capable of filling in that phase diagram and accurately predicting the structure of hydrogen's various phases? So far, the only techniques that have been developed to handle hydrogen at high pressures are ab initio molecular dynamics techniques, which are molecular dynamics techniques that are based upon a potential energy landscape that's produced by density functional theory, which is a mean field theory for electrons. But as you can see from this plot up here, density functional theory-based techniques differ dramatically from QMC-based techniques for phase boundaries. It's expected that QMC techniques should be more accurate. And so you see here that this phase boundary for the liquid H2 to liquid H transition produced by DFT is significantly different from that produced by QMC. In fact, if you look very closely, they differ by over 100 gigapascals and over several hundred Kelvin, which is a lot if you actually sit down and think about what those units mean. The reason why these ab initio techniques do so poorly is because they tend to leave out such things as zero-point motions and nuclear quantum effects, which, as in one of my introductory slides I told you, are actually extremely fundamental to the hydrogen molecule. What they also tend to do is they tend to predict structures, tend to guess at structures rather than predict them, which means that, let's say you apply these methods to a phase whose structure has never been seen before, these methods would completely be unable to predict what that structure actually was. Thus, what we want from a technique is a technique that properly accounts for nuclear quantum effects and zero-point energies, and very importantly, can predict crystal structures at high pressures given absolutely no prior information. The technique that we came up with is constant stress quantum Monte Carlo, which is a combination of two methods you've probably thought of before or heard of before, Parrinello-Rahman molecular dynamics and path integral Monte Carlo. The first technique that constant stress quantum Monte Carlo is based upon is Parrinello-Rahman molecular dynamics. And the basic idea behind this technique is quite simple. If you want to go from one tightly packed structure, like this, into a final tightly packed structure, like that, you can go between those two structures, not simply just by sampling particles and their positions, but you must also change the box size and shape in which those particles are located. So if you want to rearrange a structure from here to there, you must allow the particles to sample spaces that are larger than the original spaces. The second technique that constant stress quantum Monte Carlo is based upon is path integral Monte Carlo. So there's a lot of math that's involved here that I don't want to go through today, but the basic idea is that path integral Monte Carlo is a stochastic way of calculating finite temperature properties of quantum systems, such as their pressures and their energies. After you do go through all of the math, what path integral Monte Carlo suggests is that you can represent a quantum particle, let's say quantum hydrogen, by chaining some number m of classical particles together, and each of those particles represent a different time, and then chaining them together like a spring. So if you wanted to represent quantum hydrogen, for example, you could represent it by 3 classical hydrogens chained together by springs, such as here. Our constant stress quantum Monte Carlo technique is a combination of these two techniques in which you basically do a path integral Monte Carlo simulation, but in a box that changes shapes and volumes at different times so that the particles can rearrange themselves into the appropriate structures for their various pressures and other external parameters. So in conventional path integral Monte Carlo, you would put quantum particles in a box, but that box would be fixed and rigid throughout all time. However, in constant stress quantum Monte Carlo, you would put quantum particles in boxes that can each individually change their shape and size at all different times during your simulation and at all different times at which these classical hydrogens are located. What this boils down to are 4 very basic moves that you use to sample your partition functions and your other quantum observables. These are single particle moves where you move single hydrogens, multi-particle moves where you move multiple hydrogens on a chain, single box moves where you move single boxes at a single time, and multiple box moves where you change the shapes and sizes of multiple boxes individually at different times in your algorithm. Today, I'll show you one very, very quick example and simple example of what constant stress quantum Monte Carlo does, and I'll apply that to a quantum hard sphere model. Unlike hydrogen itself, whose interactions depend upon the positions of the hydrogens and the orientations of the hydrogens in a very complicated way, I won't go through this potential. The hard sphere potential is quite simple. It's very much like billiard balls in the sense that particles only interact when they come very close to each other and repel one another. So quantum hard spheres are a simpler computational model, and their structures, for the purpose of this talk, are easier for you to visualize. Just think of the crystal structures they might form as the structures that would form if you put marbles in a box and compress that box. Those would be the same structures that quantum hard spheres would form. But also, interestingly, for our algorithm, quantum hard spheres happen to be the most challenging test because of the fact that quantum hard spheres repel each other so strongly and therefore cannot rearrange easily. So as a first test, just to show you how this works, I applied our algorithm to an FCC structure. So I placed quantum hard spheres in an FCC structure, and then I allowed that FCC structure to deform into a liquid appropriate for its given parameters. So I put 108 quantum hard spheres in a box, each composed of 100 classical hard spheres, and then allowed that box to deform until it achieved the appropriate volume for its conditions. And as you can see here by my squiggly lines, after some equilibration time, eventually my algorithm concurs with previous results which are given by the straight lines for 5 different densities that correspond to 5 different pressures. You could also look at this from the energy perspective and see here I sort of changed up this plot. Now I'm using the highest possible densities to which I can do this deformation. You can see that my energies also agree. But if you have a very, very, very good eye, you might see that my energies for the highest densities are a little bit off. And this is because at the highest densities, I'm not quite actually in a liquid phase. The final phase is a loosely packed solid. And so if you think about a loosely packed solid, you cannot sample that solid's configuration space just by doing single particle moves. Because in a solid, all of these single particles are surrounded by cages of other particles. And so individual particles can't move that well in a single cage. And so in order to remedy this and to bring our algorithm to get it to do what we hoped it would do, I supplemented my move set with cluster moves. In a cluster move, I randomly select a particle and then move it until it collides with another particle, and so on and so forth, until you move all the particles a distance L. And in this way, you can move a coherent set of particles in one specific direction and thereby actually sample your configuration space as opposed to randomly moving individual particles up and down so that they may not coherently move all together. In this way, you can overcome the previous ergodicity issues that I discussed before. So putting these together into our algorithm, I did the supreme test of our algorithm, which is can we get a crystal structure, a BCC crystal structure, and have it transform into a different solid FCC crystal structure just by using the moves I suggested. And so what you can see here is for 32 quantum hard spheres, if I just do particle moves, individually moving different particles, the FCC order parameter I have remains very low, which indicates that I was not able to rearrange this into an FCC crystal. However, if I use cluster moves, which are denoted by the red here, you can see that my FCC order parameter comes very close to 1, which means that I was able to make this transition from a BCC crystal to an FCC crystal. And what this means is that our algorithm does what it was supposed to do. It can rearrange for the hardest test of quantum hard spheres, one solid into another solid at high pressures. So with that, I would like to quickly summarize. Constant stress quantum Monte Carlo is an accurate way of predicting the crystal structures of high-pressure phases. Unlike previous techniques, it can properly account for zero-point energies and nuclear quantum effects. Currently, I'm applying this algorithm to understand high-pressure hydrogen phases. In particular, I'm trying to apply this to phase 3 hydrogen, which is a phase that's been experimentally seen, but nobody understands what its structure looks like right now. In the future, I'd like to expand it. In my next few months at Livermore, I'll be searching for things like phase 4 and phase 5, which are phases people have never seen before. And way down the road, I would like to make this simulation completely ab initio, meaning I would like to take out my pair potentials, such as the hard sphere potential and the hydrogen potential, and replace it with ab initio potential energy surfaces. So that's a long way down the road. And with that, I would like to thank my advisors and my funding over the years. In particular, I'd like to thank Dr. Jonathan Dubois, who's advised a number of DOE CSGF fellows over the years, but who has no idea who's sending him calendars every year. He has no idea. And I'd also like to thank Dr. Bernie Alder. Let's just say I would like to be as sharp-minded and quick-minded as he is at 87 at my ripe old age of 25. And I'd also like to thank Krell for my funding and everything that they do. As Ashley once thanked Krell for showing her a country girl the world, I would like to thank Krell for showing this country girl from the small town known as Brooklyn the world too. And so with that, I would like to thank you all.